now we should move to the next teacher, Pierre Louis Frison from Paris, and he will show you the principles of radar and also optical remote sensing, but with more focus on radar for land cover and land applications. Pierre Louis, we have to decide how we manage the interaction. I know that your lectures are always very interactive and you combine the theory and the practice all the time. So differently from other teachers that do the theory in the morning and the practicals in the afternoon, Pierre Louis is alternating all the time teaching and practicals. Of course, this maybe will be more difficult doing remotely, but I trust your skills also as a remote teacher, Pierre Louis. Maybe you could also say if students can ask questions all the time, or how would you like to manage the interaction with the questions?
Did you ask me the question to me, Francesco?
Yes.
Yes, the best interaction, the most interaction, the best is. So don't hesitate when you have any question, any remark. If you can just raise the hand by Zoom or speak as you prefer.
Okay, so anyway, we will try during the lesson and see how it works. Normally, for this type of lectures remotely, of course, it would be nice to have a moderator that is maybe pointing out when there are relevant questions. And but okay, we will learn by doing. It's the first time that we do it this week, so we will improve probably the type of interaction during the day. So the floor is yours.
Maybe there is a volunteer to be a moderator.
Is there a volunteer to be moderator? Okay, Amalia is volunteering.
Oh, super.
Thanks, Amalia. Good.
Always the same.
Yeah. Okay. So, Pierre Louis, maybe you can introduce yourself. You can see what you are teaching at the University of Paris, and also hopefully establish a connection between the students so they can ask you questions also after the course, as it was the case in the past.
So thank you, Francesco, for this nice introduction and this welcome. Hello, everybody. I'm sorry to not be with you, but COVID is still going. And so my name is Pierre Louis Frison, and I'm a teacher at Université Gustave Eiffel. The University Gustave Eiffel is quite just near Paris, between Paris and Euro Disney. People may know better Euro Disney than Paris sometimes. And so I teach there, and I practice my research in the IGN, which is the National Cartographic Institute, in the IGN laboratory. And I'm focused on the vegetation monitoring with remote sensing data, and especially with the radar remote sensing data. But we use also optical data. So for today, as Francesco told you, I will make a small introduction about optical data, because the aim of today is to give you the skills to manipulate data, optical and radar data. So optical data are quite of immediate use, because we are accustomed to such data. Our eye operates in the same wavelength. While radar data, you are in the invisible part of the spectrum, the electromagnetic spectrum. And so a lot of people are a little frightened about this kind of data. And my objective today is, at the end of the day, everybody will able to use and play with Sentinel data. Sentinel-2 for optical data, Sentinel-1 for radar data. And so, as Francesco told you, I will alternate between theory and practical. More theory this morning, less this afternoon, and we are going to process Sentinel data in order to produce vegetation cartography map, a map of different types of vegetation. This will be made by supervised classification, and so we will do it together. Of course, so I'm going to share my screen. So I first make a quick presentation about optical data, optical remote sensing. Because as I told you today, we will process, we will use optical data and radar data. An important comment: I'm a teacher. It's my job, and so I'm open to any remark, any comment, any question. Presently today, but also after next week's, next month, no problem. Just you can send me the mail you want. Just I don't know your name. Present you in the email, and I'm happy to answer to all questions in my domain of skills. And so don't hesitate. So first, a quick presentation about optical remote sensing, and then I will switch and focus more on radar data. So this is an impressive illustration of remote sensing in general that has been made by optical data. This is an image that has been acquired during the night. So, do you have some comment about this image? There are different things. Of course, it's very impressive to see the night. We see the light that is used by the humans, and you see that it's better to live in some part of the world than others. But how many can an astronaut is he able to see the Earth like this when he's on the special international space? What's the name? When he's in space? Is it possible for him to see the Earth like this when he just make one turn around the world? No? Yes? All right. So first, of course, the Earth is not. The night is not on the Earth at the same moment, so at least you need two images, two acquisitions to get this image. But you have another really striking comment, a striking feature of this with this image, and you have the same here when you look at the day. Oh, it will be. Do you hear me? It's okay? Oh. Hello, hello. Do you hear me?
Yes.
Yes? All right. So if you can see, the Earth is never seen like this, huh? Because there is important thing that is missing, and these are clouds, all right? And so clouds are really present in the tropical region, as well as high latitude regions. And so you need a lot of image to get the pixels when to acquire a pixel when there is no cloud. And this image it has been acquired by sensors from NASA, and they need about 1 year of whole acquisition to get such an image, because you have cloud everywhere, and over tropical region, for example, you need about 1 year to get over each pixel of tropical region no cloud. So it's the reason why we speak about image and not photos. A photo is just an instant picture, and an image is a lot of photos that have been processed. Also, we speak about image because in optical data, even in optical data, we use invisible channel that our eye cannot see. It's wavelength that is not sensed by our eye. And so it is the reason why we speak about image, remote sensing, and not photos remote sensing. So I will pass this just if somebody knows here you have the Asia, and this is the same on Google Earth. All right, you see the frontier of between North and South Korea, and above all you have something here that is where it is. That is here in the ocean, and you can see that it appears to be a land in ocean, but it's not ocean. It's just fishing boats, and you have an idea of what does mean overfishing. So these are some variables that are that can be estimated by remote sensing. It is not exhaustive. I just put in color the variables that can be estimated with optical data. So you see, you can study atmosphere, oceans, land surfaces, and cryosphere. And with optical data, you can get information about clouds, concentration gas in the atmosphere, color of the ocean. That is really interesting for to analyze the composition of the water. Over land surface, topographic ground movements, albedo. Albedo is the reflectance, the part of the reflected radiation by the Earth over the incoming solar radiation. The type of vegetation, the different type, and the wetness of the vegetation, land use, the cartography of every part of the world, and especially in urban cartography. And also some information about the distribution and the ice dynamics in the cryosphere. So the concerned domains, there are much more now. At the beginning, it was special dedicated domains, but now you have a lot of people who, a lot of professionals in all domains that are using remote sensing. Just two words, you have two types of orbits, one geostationary and one heliosynchronous. Geostationary means stationary with respect to the Earth, and in that case, physics law show that the satellite has to be at a precise distance of the center of the Earth, and this distance is 36,000 kilometers, which is quite far. And so with a geostationary satellite, you will see the Earth, but from far, and so you won't have a nice spatial resolution about several hundred meters. And this image from geostationary satellite, you can look at them every evening at news every day now with all these information channels, and so these meteor images are seen every day, and it's very nice to have a global view, to have high temporal acquisition rate. You have now one image every 15 minutes by the Meteosat second generation satellites. These are from European countries, and the satellites are located on the equator. It's a physics law. A geostationary satellite has to be on the equator, and here in the Gulf of Guinea. And so when you have one acquisition every 15 minutes, you get 4 acquisitions per hour. So about 50 images for one day, and so it's it's okay. 12 hours of day. Multiplied by that, all right, about 50 images a day. And so when you make the movie, you see all the clouds that are moving, and it's helped a lot the meteorologists. You have low spatial resolution, several hundred meters, about 300 for MSG satellites. And as the Earth is a sphere, you have a much better resolution at the equator and a much lower at the high latitudes. The other orbits and all the other kind of, or most of the other kind of satellites use this orbit, especially the Sentinel-1 and 2 satellites. This means heliosynchronous orbit. The heliosynchronous means that the orbital plane has always the same direction than the sun direction, and so as long as the Earth makes a revolution around the sun during the year, the orbital plane moves at the same speed, and so it's a quasi-polar orbit, and it's much lower than a geostationary one, about between 700 and 800 kilometers. And with physics law, when you look at something which is turning around the Earth at this altitude, it makes about 14, little less than 14 orbits per day. And so here is the acquisition of a sensor, a low spatial resolution sensor with a swath of about 2,000 kilometers that after one day of acquisition on heliosynchronous orbit. You see he has maybe quite all the Earth. You have some gaps at the equator, of course, not at high latitudes. And so you have a homogeneous geometric acquisition, whatever the latitude you are. Poles are seen in the same geometry than equator. You have the same solar illumination, and but you have some the disadvantage is you have to wait to have a global cover, while with a geostationary satellite, with 3 satellites, you have the whole image of the Earth every 15 minutes. Here you have to wait, and but it's really used because also the same point is seen every time at the same local time. So if heliosynchronous satellite sees Riga now, the same satellite, the next time it will see Riga, it will see Riga at 10 a.m. So it is in the same condition of illumination by the sun. If we don't mind about the seasonal variation, which are important. So just some information about spectral information. So this is the electromagnetic spectrum. It comes from astrophysics book. And in astrophysics, when you look at the sky, you use all these wavelengths. In remote sensing, you don't use this because these wavelengths, these radiation are totally stopped and happily totally stopped by the atmosphere. And so remote sensing begins in visible parts, 400 nanometers, up to infrared and radio waves. And so optical data means concerns the electromagnetic spectrum from visible to infrared up to 5 micrometers. It is observed, illustrated also in this slide. The optical domain corresponds to the visible part, so the part that is sensed by our eye, but also all the wavelengths that our eye doesn't sense in the infrared, mid-infrared, far infrared, up to 5 micrometers. After 5 micrometers, the solar illumination is lower, becomes lower than the natural emissions of the Earth. And so this is the frontier. So optical data and optical sensor use from 0.4 up to, I don't know, several 1 micrometers, I don't know, we will see with the Sentinel-2. And when you get with higher wavelength here, the natural emitted radiation is still higher than the solar reflected radiation, but is low enough that we have the technology to illuminate and to highlight the Earth from the satellite with a spotlight, but an invisible spotlight. And this is radar remote sensing, and radar, which it's denoting active microwaves because you use your own illumination, and this is an invisible spotlight for wavelengths higher than 1 millimeter. So just to look, I forgot. Just here to see this is the radiation, that the solar radiation that is arrives on the Earth, and you see that most of solar radiation is emitted in the visible part of the spectrum, the wavelengths that are seen by our eye. And you have some opacity, some wavelengths where the atmosphere is totally opaque. And so, of course, if we are interested in land surface remote sensing, we use what we call atmospheric windows, those wavelengths where the atmosphere is the most transparent as possible. So here is just the difference between optical and a big difference between optical and radar data. With optical data, you are very sensitive to clouds. And when you are interested in regional tropical region monitoring, or also high latitudes, you have a lot of clouds, and so this is a big limitation of optical data. While with radar data, you are not sensitive at all because the wavelengths are higher, and so the small particles of the atmosphere and of the clouds are not seen by wavelengths higher than 2 centimeters. On the difference, by contrast with radar, in optical domain, we look a lot what we call the spectral signatures. The spectral signatures are these the signature of the reflectance. So the reflectance of a surface is just the ratio between the reflected part of the solar illumination over the incoming part. And so when you look at the evolution of the reflectance with respect to wavelength, you see these kind of spectral signatures. Spectral because of the you move on the electromagnetic spectrum. So, for example, here you can. Do you see my my mouse? Hello, hello. Do you see my mouse?
Yes, we see it.
Oh, super! Thank you. For example, when you see this spectral signature, you see that this corresponds to a particular bare soil, and you see a quite linear behavior of the spectral signature. What you have to know is you cannot guess the signatures. Is totally experimental. It's very difficult to have a theory because, as you can see, for example, here you have at this wavelength you have this is vegetation. At this wavelength, all the radiation is or most of the radiation is absorbed, while here it is quite well reflected. So you cannot guess the type of reflection at one wavelength if you know the reflection, the reflectance in another wavelength. It can change a lot, and so this is this characteristic. This characterizes the nature of the surface you are observing, and this is the only information we can get with optical remote sensing, the spectral signatures or the reflectance in one sum of wavelengths that have been that are in which the sensor is operating. So here you can see that water here is has a very low reflectance, so absorb most of the incoming solar radiation. And so when you see it from a satellite, it's dark. If you have here something, it should be the snow that is white because it reflects most of the solar incoming radiation, at least in the visible part, in the what see our eye. And you have also something very characteristic and which characterize totally vegetation. The vegetation you see here, it's spectral signatures. It absorbs in the blue and in the red and reflects a little more in the green, the reason why we see vegetation in green. But above all, what you see, you have a huge contrast with vegetation between the red here, which is really absorbed, and the near infrared, so the wavelength, invisible wavelengths, but just near the red. But here you can have a very high reflectance in the near infrared. And so this is so typical, and vegetation is so important for humanity that since the beginning of remote sensing sensors, remote sensing history, it began in the years 70. And since the beginning, all the sensors was focused on visible, of course, but they always put another near infrared wavelength of acquisition in order to sense much better the vegetation. And so we will use I speak a lot. Are you still alive? No, nobody moves. Yes, I see some movement. Is it okay? You
Yes.
listen to me well?
Yes.
All right. So it's Amalia who is answering me. Who is answering me?
Me.
Who are you? No, I don't. But I just have a voice, a nice voice. Maybe I will have the face later. So just I think you have a break. When is the break for? When is planned the coffee break for you?
10:15. 10:15.
10:15. All right. In
Yeah,
15 minutes.
but I would like to see some interaction because otherwise
Yes.
it's just from your side. I would suggest that somebody can ask questions on all the things that we mentioned so far.
I totally agree with you, Francesco, and I think you have to help me.
Yeah,
Because
so I understand. Yeah, normally during the coffee break and the icebreaker, it's easier to start the interaction because then people know the teachers and then you understand that you are human and they can talk to you. You are not just a virtual image over there, and
Yes.
you are very friendly and you don't aggress people asking questions.
I try to.
So I don't know if people here are so experienced that everything is trivial and therefore there are no questions. But I guess that even if things are, yeah, okay, good. There is a question over there. Please.
A question about the illumination. Can you hear me?
Yes.
Great.
I
So
hear you.
in some previous slides, you said the orbits or the satellite orbits are designed in a way that you have constant illumination over a particular area.
Yes.
So first of all, I'm a data scientist with Capacita in Estonia, and I work a lot with image translation between SAR and optical satellite data. And usually this illumination is not constant. It's very hard to to standardize these images across multiple dates. So if the assumption on the design of the orbit is that you're going to have constant illumination, then you never have constant illumination in practice.
No,
Exactly.
sure.
So how would you say, or what's the best way to ensure?
It was thank you for your question. It was a very what are the data you are using in optical in optic?
Usually the Sentinel-2 RGB NIR bands, and then for this for SAR the VVVH, and then the coherent. Yeah.
So it was a very bad way to introduce this, because of course the solar, if you have the same acquisition at the same local time during 1 year, you won't never have the same solar illumination. Right? You have a lot of differences. So, but it's a way to have the to have the lowest variation in solar illumination. If you make acquisition at 10 a.m. and at 4 p.m. for example, you will have much more solar illumination variations. So of course you will have a lot of solar variation, but it's the way to have the most as similar as possible solar illumination from at least one acquisition to another one for 2 weeks when they are spaced for 2 weeks, for example. And this is for visible data, and with radar data, if you give your own illumination. So this is one of big advantage of the radar. You have always the same illumination configuration. Did I answer to your question?
Not entirely, because again with the radar data, like you said, it's easier because illumination is not really a problem. But then with again optical data, especially in Europe and other regions where the sunlight differs a lot, especially with the different seasons, then it's very hard to maintain consistency with the images that you've been captured. And also from Sentinel, the images are not corrected in that sense. So every time you get images from Sentinel, then you have to apply extra correction on them to make them stable, and it affects the models that we use, and that's what, like, one really big problem with the modeling, and that's why I'm asking.
Yes, I'm totally agree with you, but for optical data, you say you have some problem also with radar data?
Data is perfect. There are no issues there.
All right. This all right. So no, with optical data, this is a huge problem. And even in the best configuration, which is heliosynchronous orbits, where the acquisition is always at the same local time. Even with this, you have big problem to have a data series which is homogeneous and corrected of the variation of solar illumination. This is sure, huh? It's a big problem. Is it okay? What I understood your question.
You did fully.
All right.
Thanks for your response.
Thank you. I will stop to speak. We will just after the coffee break, we will manipulate some Sentinel-2 data. So just to finish with the spectral signatures, you have these spectral signatures, and I told you that vegetation is very typical spectral signature. It absorbs in the red, reflects a lot in very close wavelengths in the near infrared. And so we use some contrast index to discriminate vegetation. And the contrast in this index maybe either the reflectance acquired in the near infrared divided by the one acquired in the red wavelength, or the reflectance, or the difference between both, or also when you normalize, when you make the difference over the additive sum of these two reflectance, and these are called vegetation index. We are going to compute it with SNAP just after the coffee break. Just another thing to finish is before the coffee break, just how do we get the colors? The colors, you just acquire the same scene at 3 different wavelengths, and this is wrong. I think this is better 600. So when you acquire the same scene in different wavelengths, our eye is able to visualize 3 different wavelengths. Our mind is just close with 3 dimensions. And so with 3 different wavelengths, if you image the first one at 400 nanometers in blue, the other one in green, and the other one in red, you can get this family photo, and so it's okay when you see that this dress absorbs a lot in the blue, absorbs a lot in the red, and reflect a lot in the wavelength that we see in red, and so it is the reason why you see it in red here. And so this is the visible perception of photo. It's okay, all right. But now when it's exactly the same with the sensor. It acquired in different wavelengths. And after, when you have an acquisition, you just visualize with the software in 3 different colors. So for example, this is an image that has been acquired by a remote sensing sensor. And if you visualize it in the same way than our eye, you have a picture. And now, if you, of course, if you want to see the near infrared, the invisible wavelength, you can colorate it in whatever the wavelength, the color you want. And the standard visualization is, in order to discriminate well the vegetation, is to visualize the near infrared in red here, the red, this wavelength that we see, our eye sees in red, we look at it in green, and this wavelength that our eye see in blue, we visualize it in no, this one, our eye sees it in green, we visualize it in blue. And with this standard visualization, you will see all the vegetation in red, because of course the red corresponds to the near infrared wavelengths where the vegetation reflects a lot. So this is the visual observation, and this is the standard false color composite image that it is used, and that we will see just near after the coffee break. So we stop now for the coffee break. For how long does it last?
30 minutes.
30 minutes, all right. So we see us in 30 minutes, and we will just manipulate some Sentinel-2 data with Snap.
Pierre Louis, we have one question for you.
Yes.
In previous slide about reflection, there you have in grayscale reflection. Can you go back to the slide with reflection?
This
Yeah,
one?
no, back. Yeah, this one. You have here you have reflection bigger than 100%. No, maybe I haven't heard. There is description. So on the left there is reflection in percents, and you have bigger.
All right. Excuse me. The dark part here corresponds to the opacity of the atmosphere. The white part here corresponds to the atmospheric windows, and are the spectral signatures are these curves here. All right.
So lines is reflection, and this
lines are spectral signatures.
Yeah.
The reflectance in function of the wavelength, and here the dark part corresponds to the opacity of the atmosphere, and by contrast the white here corresponds to the atmospheric windows. It's okay?
Yes, it's okay.
And I have, for example, here maybe it's better. Here it's just spectral signatures, so reflectance of different type of surfaces with respect to the wavelength. All right?
Yes, all right.
Do you have any questions, additional questions or comments?
I don't think anybody else has other questions.
So enjoy your coffee, and see you in
at 45.
45, all right, super.
Okay.
Thank you.
We'll tell you as soon as the data have been downloaded, so you can then switch from the theory to the practicals.
All right. Super.
Okay. So the floor is yours.
All right, thank you. So just some, I have to share again my screen. So just we stayed on how we see the invisible, and the standard way to look at one invisible wavelength, the near infrared, because it is very discriminative about vegetation, is to look at near infrared in red in green, and green in blue. And you have this kind of image, which is largely used even in newspaper and news on TV. Now, when they show some remote sensing image, they show you this without explication, so it's quite common now. Just here to some study case over a very rich part of town in America, when they have a nice cottage. You see it, a photo here with the near infrared channel. You see it very well. And what's the point on this illustration? No. A striking feature on this illustration? Nobody? What about the stadium? this is the grass of the stadium is not vegetation. All right, and you see it very well in the infrared channel. This is synthetic grass, widely used now. So of course, here, for example, a Landsat image, in 3 different channels: red, near infrared, and middle infrared. So 2 invisible channels here. And you can see it in the color composite that you want. It's so you will have false colors that we call that is called false colors. Here I heard that a part of you are concerned with forestry. You can discriminate between conifers and broad-leaved trees with infrared also. There are much better illustration now. I didn't get time to take it. And if there are some geologists in the class, the invisible part of the spectrum is really interesting over bare surfaces, over rocky surfaces, due to some signatures of typically typical rocks. And so, for example, here, over Atlas in Morocco, the beginning of the mountain in Morocco, you have here, it's with a MODIS image, Aster image, an American NASA sensor, with just by the use of these different wavelengths, totally invisible, but which are able to characterize a lot the different type of crystals. Not crystals, I have forgotten. You have this, with this image, you have at the first glance a geological map. So it's really spectacular. Such a geological map is difficult to produce. You need to go on the terrain and to be a geologist. While here, at a glance, you have it. Of course, you need to be of a bare soils. If you have some vegetation, such type of maps is impossible to do with a geological composition. So these spectral signatures are really used. Here it's all the channels used by the NASA sensor, well-known, which is MODIS. It's a low spatial resolution between 250 meters and 1,000 meters, depending on the channel. And you see, you have all these channels corresponding to narrow spectral band, and each spectral band corresponds, is needed for the analysis of typical features. These for clouds and aerosols. Here, all these channels, all these wavelengths for ocean color. Here for again for the atmosphere, and so on. Some images from the geostationary GOES satellite, the American satellites, equivalent to Meteosat second generation for Europe, and the same seen in visible and infrared parts. You see different things, and when you make a color composite, you have this. And of course, you can have a lot of information about the type of clouds, their temperature, altitudes, if they are precipitative clouds or not, and so on. So here are some different sensors. NOAA AVHR is a NASA satellite, an American satellite from the NOAA and National Ocean and Atmospheric Administration. And it is a really important one because it begins in the 70s. You have acquisition without interruption since the 70s. And so you have, it's a low spatial resolution sensor between 1 kilometer to 16 kilometers, and you have a temporary visit of a week. Then you have the ESA sensor and the NASA sensor MODIS. MERIS and MODIS are quite similar, approximately the same resolution, the same temporal revisit, and similar bands of the spectrums are acquired. Now MERIS is over, and it has been replaced by the Sentinel-3 satellite at low spatial resolution, several hundreds of meters. Landsat, this is a very important satellite because he has been acquired since the beginning of the 80s, I think, every 15 days, between 15 and 30 meters of spatial resolution. And so when you are concerned with the land surface evolution for a long period, the largest period for remote sensing, it's now about a little less than 50 years. But when you are concerned with this, you use, of course, Sentinel-2 data, which are magical data, incredible, but it has begun only in 2016. And if you want to see how the land surface is evaluate since before, you compare with Landsat observations. Aster also, but you don't have so many acquisition. Spot, all right, it's a French one. You have to pay, and so it's not so important. Oh, you have to pay, but with the ESA third part mission, I think you can get it now for free at ESA, but before you had to pay. And of course, you all know better than me all these satellite sensors with a very nice resolution, lower than the meters. Iconos, for example, so you have to pay, but if you want to have some samples, you go to Google Earth and you can zoom and see what we see with lower than 1 meter of resolution over the cities. So here I continue this catalog, and I finish, of course, with Sentinel-2 data. Sentinel-2, which is incredible, a real revolution in the panorama of in the landscape of remote sensing data, because you get a full coverage every 12 days for one satellite, and as you have two satellites every, not 12, excuse me, 10 days. So with two satellites, you have an acquisition every 5 days with between 10 meters and 60 meters of spatial resolution, depending on the wavelengths you are acquiring the scene. And this is available for free. It's a revolution. ESA showed us the light with this kind of missions. So here, just with the well-known NOAA AVHR sensor, this is an image corresponding to the first decade of April 92 in the red channel here, in the infrared channel. So you can see that, for example, boreal regions have very high reflectance both in red and infrared channel. So you see that here, if it's high reflectance in infrared channel, it's not vegetation, because you have also high reflectance in red channel. And when you make the vegetation index I was telling you, so you just subtract the red reflectance to the near infrared reflectance, and you get this image. All the snow, the clouds have disappeared, and what is bright corresponds to vegetation, and the most developed vegetation, the whitest. Sorry, here some illustrations, but some illustrations with low spatial resolution. Here you see all this valley over the semi-arid India Peninsula. We speak a lot in France. I don't know in Ljubljana you spoke about this, about Sahara dust, because now last year and this year we get 2 events of Saharan dust who deposit over France, over the Alps. When you make ski, you see all this red color, and I don't know if winds were strong enough to bring this dust up to Lithuania. Here, another Saharan dust crossing the Atlantic Ocean. It is very important for the fertilization of the ocean, all this organic matter. Some Namibian desert here with Modis. So these are some illustration. This is with Meris, and this is the Bengal Delta, and you see all the erosion reversing in the sea. Here the Caspian Sea with Meris data, and this is very important to this image. Show you why so many people are analyzing the color of the ocean. And for example, when you have a pollution, to know if it's organic pollution or chemical pollution, if it comes from some algae or if it's a chemical reason. And so here, a Meris illustration, the visible part of West Africa with the Lake Chad here, with false color using near infrared. You see, it's really meaningful, much readable for vegetation. Here, the same over the Senegal River in the Sahel. You have Mauritania here, Senegal there. And in April, you are at the end of the dry season, and you here it just looks at it's just looking at a desert, bare soil. Then in May, the beginning of rain, the color change, the soil color is changing. While here you can see that you have always culture, because you are on swampy regions, and so you have always here some cultures. But here it's at the end of the dry season, it's bare soil, and then at the end of the rainy season, you can see that the grass layer has developed everywhere. Here, an illustration of the Landsat coverage over Israel-Palestine region. No, sorry. I will change it for when I will give you the slides. Wow. So in one acquisition with Landsat image, you have all this region. So for regional monitoring, it's nice. And for example, for with spot image here, of course, you have better spatial resolution. But if you are interested in all this region, you need much more processing data because you need to make mosaicing. Yes, let's say it. Something. This is an illustration with spot data, but you do the same with Sentinel-2 data. When you get some a sensor, for example here, acquired with 20 meters of spatial resolution in 3 different channels, so you can get a color composite image. And sometimes when you increase the spatial resolution, generally you have too low energy coming from that is reflected from the land surface you're observing. And so in that case, when you want to increase the spatial resolution, as you have so low energy, you enlarge the spectral domain in which you acquire the image. And so the bandwidth here are approximately 20 nanometers, but here the bandwidth, the spectral range of acquisition covers the whole visible part of the spectrum. And it is the reason why when you have really high spatial resolution, even now for the metric sensors, when you have metric, you have just one gray color image because it acquires over the whole visible spectrum, and you can have some color image over with a lower spatial resolution. And so here it's 20 meters, here it's 10 meters. Of course, you have twice more pixels because it is the same area but with double spatial resolution. And there are some techniques that we can do to improve and exploit the difference color information here integrated for this spatial resolution. Some illustration about the use of optical data for the monitoring of disasters. Here during the tsunami in 2004. So on the left it is before, on the right after. Francesco can tell you more about this because he was involved in the policies made between all the different spatial agencies to monitor and focus on location in the Earth where you have some special disaster. Here the same with over another spot. And here some illustration about really high spatial resolution, but I removed a lot because everybody knows with Google Earth. All right, and just at least this diagram to illustrate the Sentinel-2 image characteristic. So you see that you have 30 bands which acquired in different wavelengths, and you have 3 bands at 60 meters of spatial resolution, 6 bands at 20 meters, and 4 bands and 10 meters. And so for the practical of this afternoon, we will use above all these 4 bands of 10 meters. Does the Sentinel-2 data has been copied on all the computers? Hello, hello.
Hi, Pierre-Louis. Yes, we just finished right now.
Oh, super.
What I would ask, though, to people is that they connect to the Zoom meeting if you want to start with the practical. Because some of them are watching the YouTube stream, and that has about 30 seconds of delay from what you are actually doing.
All right.
Yes? So then I'm going to put now something on the screen. If you give me 2 minutes, I'm going to put something on the screen and you can connect there. So you stop with the YouTube streaming and you enter Zoom. You have to be muted without camera, of course. So just give me 2 minutes while I set it up.
And you can run Snap. You have the shortcut on the desktop. You can launch the Snap software. It's dedicated to the data processing, remote sensing data processing, above all that has been acquired by ESA sensors, European sensors.
This is the link. Everyone, can you connect to this link? You should have Zoom installed, so you should enter the Zoom meeting. And if you're having problems, then raise your hand and we come to you. So you can go ahead. We're just helping a couple of persons.
All right, so how to get some Sentinel-2 data? You go to,
I mean, if we're already whatever, yes.
Here in Google, I type ESA Hub, all right? Open Access Hub here. And then I click on Open Hub. Then here I have to log in or register. And this is the one of the revolution I was telling you concerning Sentinel. Everybody in the world who has an email address can get all the Sentinel data for free. It is incredible. So here I am recorded, so I log in. And if you are not, you need 2 minutes to get it, but you can do it. You can just show my look at my demonstration if you don't have if you are not registered. And even if you are not registered, you can do all the things except download the data. So, for example, I made. Can you? I'm here on Riga, and here I just select my the study area, and now here I made a mistake again. All right, and now here I just look at the Sentinel-2 acquisition that have been made. So you have a lot, huh? You have a lot. So we are all right. Sensing period just from the 1st of June. From the 1st of June to today. All right. And now, all right. Product type. I just want the S2 MSI1C, S2 for Sentinel-2, MSY for multispectral instruments, and 1C corresponds to the product level. 1C corresponds to reflectance that have been recorded on the top of the atmosphere. So you will have all you will see all the clouds and all the atmospheric perturbations. Level 2A correct from the atmospheric perturbation, but for this we just stay. We just keep the project type 1C, and let's do it. You click on the. You click on the. What's the name of this? This it's a magnifying glass, or I never remember this word. And so you see all the Sentinel-2 data that have been acquired on Riga last month, during the June month. And for example, what is this? It is totally white. What corresponds? It's strange. It's strange. Maybe it is totally full of wind, of clouds. If somebody remember what happened on the 18th of June. So you have, depending on the orbit, I told you, if I look at here, I told you the orbits of heliosynchronous satellites are quasi-polar, so they are not vertical, but just a little 9 degrees of inclination, and the ascending orbit is oriented from southeast to northwest, and the descending orbit is oriented from northeast to southwest. So you see here, depending on the orbit, you have different scene that encompass the study area I gave, who are concerned here. So, for example, if I click on the eye, I have a quick look of the image. Yes, maybe it's quite cloudy. And for example, here you get one image without cloud, and you can, as I am logged, I can download it by clicking here. If you're too annoyed with the clouds, you can also here add a selection criteria with the cloud cover. If you want 0 to 20%, if you want only the acquisition with less than 20% of cloud cover, you can use this. So be careful when you do this. This percentage corresponds to the presence of clouds over the whole acquisition, while maybe you are just interested in the downtown of Riga, and so you have also to check with by looking at the data. And so when you get the data, is it okay? You have some questions? Is it okay for everybody? Everybody has can download now the Sentinel-2 data, or I went too fast?
Pierre, they are saying you went too fast, but also if these are the data you told me, I already downloaded them, and they should be in the French Guiana folder.
Yes. No, okay. In the French Guiana folder, I sent you the. I didn't send the data in the folder because you told me.
But you told me the list, and I downloaded them, and then I put them in the right folders.
Yes. Yes. All right. In
okay.
that one, sent to S2. You should find it here. French Guiana the data S2.
So this was a demo on how they could download it themselves, but the actual downloading, which takes some time, has already been done for them in advance.
Already downloaded, yes. But I just wanted to show them how I get this. So you want me to do it again?
Yes.
All right, I do it again. I close my tab. And I open it again, ESA Hub, here. No, it's not CISA, it's ESA Hub. And you get the Open Access Hub. When you get this window, you click on Open Hub. Amaya, can I be confident with you to cut me when you see some people doesn't follow and I stop? No problem.
Okay.
I know. Thank you.
Yes, let me just double check if some people. Is everything all right? Do you manage to access the website? Okay, I'm gonna go there. Yes, you can continue. I'm gonna help some people.
And just, I don't know if it's changed something. When we are going to manipulate and process images, it needs a lot of experience because everybody click on the wrong button and do stupid things, and me the first. So really don't hesitate to ask me when you are lost. It's not because you are not, it's just because you have less experience that other people get. So don't hesitate to not be totally lost, because we just stop and in order to keep most of people in the same train. So I'm here on Copernicus Open Access Hub, it's okay. So here, I do it. If I log out, all right. Here I go to, I'm interested in Riga. So I go here, I zoom, I'm here. And now I click here on this square, switch to navigation mode. And I draw a small area, the area corresponding to my study of interest. My region of interest, excuse me. Is it okay?
I think it's okay for everybody.
Thank you. So now you click here on these three lines, and you can fulfill the fields you are interested in. Now we are not interested in Sentinel-1. We are interested in Sentinel-2. The sensing period. I'm interested of all the Sentinel-2 acquisitions that have been made since the 1st of June up to today. The satellite platform, I don't care if it's Sentinel-1A or 1B, both of satellites are interesting me. They made the same acquisition and I have 5 days revisit instead of 10 days if I use just one. Product type, I told you, no, it's not Sentinel-1, it's Sentinel-2, excuse me. Here, product type. This corresponds to Sentinel-2 multispectral instruments, and the products we want are level 1C, which is not corrected at all from the atmosphere. I prefer this because, all right, you have a processing chains which correct the atmosphere, but it's not magic. You still have atmospheric perturbations, and so when I don't know, I prefer to get just the reflectance that have been acquired top of the atmosphere by this sensor with no correction. Is it okay?
It is okay so far, yes.
Click now on this magnifying glass. And to make the research, you need to be logged. If you're not logged, don't do it now because it's just 2 or 5 minutes, but you can just look at me. You log, and now I can do it again, and now it's begin its research. And these are all the data that have been acquired over Riga by Sentinel-2 during the last month of June. So you see that you have some data full of clouds because you are high in latitudes, full of clouds apparently here also. And you have other without clouds, for example, this one. If I look at what it looks like this. It's okay. It's okay. So I can download it by clicking here. All right. And when I do it, it downloads on my computer. And now we arrive to this file, a zip file coming from Sentinel-2B multispectral instrument level 1C that has been acquired the 6th of February 2018. And this is over French Guiana. This is the region over which we will make the practical today. Is it okay?
Give me 1 second so that I check. Is it okay? Oh, you are registering. Oh, okay. And you are also registering, right? Okay. So some people are registering to try the download, but I can catch up with them later.
Yes, do it later. It's not necessary to do it now.
Yeah.
You just will get exactly what I should.
You already have the data in your folder. We pre-downloaded it.
Can I continue?
Oh, yes. Yes, you can continue.
So now you go to the folder C, French Guiana data S2 that Amalia installed on your computer, copied on your computer. And inside you get this Sentinel-2 data that have been already done, that I have already downloaded last week. It's okay?
Pierre Louis, can we repeat the location?
The location is French C, the hard drive C, French Guiana data S2. It's you put it like this.
Yes, I put it like this. So I'm gonna go around.
C French Guiana data S2.
Okay.
It's okay.
I think so.
And if it's okay, it's nice. You take it and you drag and oh, excuse me. Did you all open Snap? The Snap software. Did you open it?
So they are opening it.
All right.
Not everybody has.
In order for me to be able to follow you, we are going to do like in a Formula One race. All the technician people, when they have finished, they raise the hands, you know? And so I know when I can continue. No, it was a joke. It was a joke. Is a Snap open?
Yes.
All right. So you just take the Sentinel-2 data.zip here, you drag and drop, and you put it in Snap software. You have in Product Explorer here the name of the product here. If you click on the arrow here, you have all these sub folders who are open. And if you open the bands folder, you see the 13 channels that have been acquired by
So this zip is going to be fine because they are readers.
22. Is it okay?
1 second. 1 second.
Yes, yes.
I think it is okay.
Super. Thank you, Amalia. So now we are going to have, you see, the four bands with 10 meters of spatial resolution are B2, B3, B4, and B8. 2, 3, and 4 corresponds to what our mind see in blue, green, and red. And B8 is the infrared channel. So in order to open it in a color composite image, you just go to Window here. And you see, for example, I cannot click on Open RGB image window because this has been the file has been selected, has to be selected. All right. When this is selected, you can go again, Window, and now I can click on Open Red, Green, Blue image window. Is it okay?
I think it is okay. Yes.
And so, for example, we are going the natural colors, which corresponds to the view of our eye, where channel 2, 3, and 4 are in blue, green, and red, like we do in. And when you make OK, you get this image over the Cayenne area in French Guiana, and this is a true color image. We are doing the same by introducing. We are doing the same by introducing the infrared channel. So in that case, again, Window, open. What happens? Open red, green, blue window. And now here you can select false color infrared. Again, be sure that this is highlighted. And then in Window, open RGB image window and click on here, not natural colors, that is what we did. But now we are going to make a false color with infrared. And you see, the infrared channel now is in red, the red channel is in green, and the green channel is in blue. And of course, it's much more relevant for the vegetation. You can open here you can open here you have different zoom button, and if you click on this zoom with P for plane resolution, here you have 1 pixel of the image, which corresponds to 1 pixel of your screen. And so it's the best resolution you can have. If you zoom anymore, you will see the pixelization of the image, because the pixels of your screens are much smaller than the pixel of the image. Another thing you can see. Are you okay?
Generally, yes. Generally, yes. There are some people who are a bit behind.
And the particular, I can.
So So now I have everybody with the false color image displayed.
So now you can, if you want, you can compare the same with the true color by clicking on the tab, corresponding tabs here on the top of the image. And now just I wanted to show you something. It was to show you go to window, no, excuse me, in optical and spectrum view. And we will see the spectral signatures of the corresponding pixels. Of course, spectral signatures in only 13 different bands, 13 different wavelengths. All right? And now you can see, so if I zoom a little more so when I am on vegetation, I see the high contrast between red and near infrared. And when I'm on a building, for example, I have a totally different spectral signature. Or here on water, totally different. And it is these informations that are extracted, exploited, and it's only with this information that we can do all the different application with optical data. It's incredible because it's so few, and we can do so much. But of course, so few, it's not so. it's a nice job to be able to have acquisition in such different wavelengths with such a good ratio to noise, signal to noise ratio. So, all right. And just to finish with this, we are going to compute a vegetation index. So, for example, we are going to use, I told you, vegetation index is based on the either the difference of ratio between reflectance in the infrared and the reflectance in the red. The difference is really big when you are on vegetation, while very low when you are over other structures. For example, here, I have a very high near infrared reflectance, but I have also a very high red reflectance. So it's not vegetation. So to do this, we go to raster, band mat. All right. The name of the new bands we are going to make to use Ration Vegetation Index. And you click here on edit expression. You click here on edit expression, the mathematical expression. We are going to make some, to introduce some relation, some computation between different bands with different bands. Is it okay?
Yes, it's okay, but the name of your band is RVI.
For ratio, ratio vegetation index. All right?
Yes.
And now I edit expression, and I just take the infrared divided by the red, and the red is the infrared is the 8th band, and the red is the 4th band. And you have to see, okay, no errors here in green. It means it's okay. All right.
So band 8 divided by band 4.
Yes.
Because this, I repeat because the screen is a bit small.
All right. All right. Thank you, Maya. And if you do it, you can close the window of the spectrum view, and you can compare. If I zoom in plain resolution, you can compare, and everything that is white corresponds to the to vegetation, because it's you have a high ratio. So just, is it okay?
Yes.
All right. So just to show you now, you have optical and you have thematic land processing. And when you go to vegetation radiometric indices, you have a lot. And what we did is just RVI processor, Ration Vegetation Index. All right. Just I show you your. It's not. You can do it if you want. If I choose it again, in tools now, in opticals, thematic land processing, vegetation radiometric index, and RVI processor, if I do it,
Pierre Louis, can you show again where you saw it? Where you find this index?
yes, just I stop the computation. Don't do it because it takes time, but I will show you. Okay, it's okay. And there's been open in Snap. Okay. Again, I go to optical, thematic land processing. And now in vegetation radiometric indices, you have all different type of vegetation indices. And I choose the RVI processor, which corresponds to Ratio Vegetation Index, which is exactly what we compute with the raster calculator. It's okay? In optical, thematic land processing, and vegetation radiometric index. Is it okay? And now this is the ratio vegetation index. No, the band that I have calculated, it is here. So there is just one band, which is the RVI. And if I double click and I zoom in plain resolution, you can compare, and you just have different of, you just have, it is just the histogram, which is, wait a minute, 95%, RVI, 95%. it should be exactly the same because it is computed like this. All right. If you want to know how it is computed, you go to thematic land processing. You take this RVA processor, and when you click on help, it gives you the formula, and it's just near infrared over red infrared because the factor for infrared are chosen for S1. And now, one of the most used, the vegetation index that is the most used is not the ratio vegetation index, but is the normalized vegetation index. Where it is? Here, the second one. Normalized difference vegetation index. So based on the difference and not the ratio. So the difference is just infrared minus red. And as it is normalized, it is over infrared plus red. I just show you. All right. Here are the difference, the most commonly used vegetation index. The vegetation index, the widely used throughout the world is the normalized difference vegetation index, infrared minus red over infrared plus red. So these values, it's nice because they are comprised between -1 and 1. They range between -1 and 1, while the others can have a lot of different have range values much more extended. Is it okay?
It seems okay, yes.
All right. So we are. It is time to lunch now. Is it this? Amalia, the lunch is.
No, I was thinking. Yeah. What time is it? 4 minutes. Okay.
I'm not wrong.
I think at 12 o'clock we have the lunch. So unless you have something for the next 4 minutes, we could make the break.
I didn't speak about radar, and so this will be for the afternoon. What did I wanted to say? I think it's better to begin with radar this afternoon. Huh? What do you think, Francesco?
So I think it's very important for us to have a proper introduction to radar remote sensing. It was the main focus of today's lecture by Pierre Louis. So if we manage to be back at 1:10, so we really start with the SAR remote sensing lecture at 1:15.
Super, Francesco, super.
Is there maybe one question you want to ask before we go out for lunch or not? Yes, there is one question over there.
Thank you. The question is about how different is computing these NDVI indexes in SNAP as compared to like taking actual raw values from Sentinel-2 and computing them, because sometimes the Sentinel-2 has very dynamic ranges, especially the NIR bands. It has very high ranges sometimes, and it can easily affect when you're doing like raw computation, and it's difficult when you're trying to scale the values towards specific ranges, and I never get consistent values personally. So how would you say these are different?
You made the comparison before?
Yeah, I didn't. I made the comparison before, and the ranges look very similar in this case, but in certain cases, when you have, for example, with Sentinel-2, you can either have the dynamic numbers, which is the infinite range from 0 to 12,000 and above, or you can have the values between, say, scaled between 0 and 255. So if you compute NDVI with 0 to 255, and they're high intensity values, then you're going to have very saturated images. Everything appears white because you're not seeing the full picture. And there's not a fixed range of values for the red, green, blue, and NIR bands.
If you have differences, this is due to computational problems. Maybe because an error that comes often, maybe it's like this, I don't know, I should see with you, because it is because if you make some computation and your data are in integer, for example, if you divide an integer with another integer, you, instead of getting a real data, you will have 0, for example, because it computes this as if it is an integer also. So this often introduce big errors. And now, if you don't have this, normally you have exactly the same. It's NDVI is NDVI. So maybe just let me check something. Yes. So after another something that can change is that normally NDVI is with infrared factor and red factor equal to 1. Maybe sometime, but no, I don't think by default it's 1. So if you have changed a little these values, you will have some different values, but normally you have exactly the same.
Okay, I'll find some examples probably later on and show, because I think SAR has the same problem with dynamic range. There's no fixed.
If you can crop a small area and send it to me by email, I can look at this during the lunch break. Okay.
I don't have an example now, not from this exercise, but from other things. So I'll do that later on, if that's okay.
Whenever you want. If not today, tomorrow, I will be pleased, tomorrow or next week, or as you want. I will really pleased to answer to this, because it shouldn't. Yeah. And so we have to find the explanation.
All right, thank you.
Is there any other questions? So,
hello. Question here. In Snap, how do you see how can you see value of each specific pixel?
By clicking on Analysis, and then you have somewhere, maybe here, you have somewhere a pixel info. I thought it was in a view. Ah, yes, excuse me. Tool windows, in view, tool windows, and you get to pixel info here. Is it okay? In view, tool windows, and pixel info.
Ah, in view, okay.
Is it okay?
Yes, thank you.
And now you get the values of all the bands that are displayed in these windows on the right. you have all the values corresponding to the pixels under the mouse.
Yeah, thanks a lot.
You're welcome. Do you have any other questions? And why don't I have area? I know. All right. Do you have any questions?
So I think there are no more questions.
So
So then we move for lunch and we start again at 1:15.